Okay, so this morning we're looking at section 1.2. Yesterday we looked at conjectures, or how to make ideas after looking at examples or multitudes of examples and then making some sort of a statement that you think will work for all cases, right? Um, we also said that sometimes you could prove those statements to be false. And today we're looking at the validity of some statements. Okay, so we're looking at how can we prove statements wrong? How can we do some of this stuff? Did anyone come up with a conjecture about diagonals AB and BC? Did anyone say anything about this? You're saying these two lines, line AB does not equal line BC. Okay, that's a statement Demira is going to make about this thing. Okay, let's go with that statement. She's the one that spoke up. Now, if we take our rulers, you guys know how good I do with rulers on this smart board, hey? If we take our rulers and we measure from this point to here, oh, do I want to measure in inches? I guess I am going to be measuring in inches. Am I right on the line? I'm not right on the line either. But 2 1/8 of an inch, right? If we're measuring inches, if I scroll this thing over, I get what? 2 1/8 of an inch. So what did we just do to Demira's conjecture? We just proved it wrong, right? So what we did, they might physically look like they're not the same length, but because they're on different angles, right, they are actually the same length. So by measure, they are equal. Okay? Now, I don't know if looking at the paper, but looking up here on the smartboard, do you want to make a conjectures about these lines? Oh, so you're saying the lines are equally spaced? Is that what you're trying to tell me? Lines are equally spaced and they're actually lines. So they are straight lines that are equally spaced apart is what you're telling me. You guys agree? Jesse's conjecture, these are straight lines and they are equally spaced apart. Okay, so I'm going to pull my ruler down here. Okay, come here, little ruler. Okay. Okay, so that looks like it's pretty straight there. Straight there. Even coming down here. Does it go straight across? Yeah. I agree with you, Jesse. We're not proving you wrong by doing this, but we're proving that we can't prove you wrong right now. So equally spaced, what does that mean? That the lines, if I turn my ruler this way and we take a measurement, they're all going to be measuring the same distance. So that's 0.7. So next one, 0.7. It's really hard to see in this thing. 1, 2, 3, 4, 5, 6, 7. This one's 0.7 from here to here. 1, 2, 3, 4, 5, 6, 7. This one's 0.7. So if they're all 0.7 centimeters apart, they're also equally spaced. Okay? So he made a conjecture. Lots of times people say those lines are curved. Why? Because visually they played around with the different colors and shading and, well, not shading, just black and white, and it doesn't look straight. So lots of people will say those lines are curved. And then you can go prove them by just doing this ruler thing. Here, we tried to prove him wrong. We couldn't prove him wrong. So his statement stands right now. Okay? Notice I said we didn't prove him right. We tried to prove him wrong, but we didn't, so his statement stands. Okay? You can never prove right. You can only prove wrong. Okay? Okay, what about the number of triangles here? How many triangles are in this shape? Morgan says 2. Okay, so Miss Kelly, how did you get 8? So you're saying like this big one here? Okay. The whole red one, that's 2. Here, here, and here. Here, here, and here. So that's 6 plus the 2 big ones, which make 8. Okay. So that could be a proof of why you think it's wrong. Okay, or why it doesn't work. Now, there also could be 14. Someone could say there's none. Why? Because the lines are not closed, right? Triangles are three-sided shapes. These ones don't actually have complete sides, right? None of them that you guys showed me have completed sides. Okay? So they can be proved wrong by many different cases. So for example, someone might say there are 2, right? Those 2 big ones, right? And they'd be okay, because sometimes it just is how you visualize and how you see things, but then you have to have those statements to back it up. Okay? Christina. Well, to me, that white one is just empty space. It doesn't have any sides, because it actually flows out into here, right? And flows out into here. There's no actual line there to saying that's a triangle. You can just visually see that shape. But it depends on who you are and what you say, right? It's just like shadow games. Is this okay? You guys all right with this? So, some quick statements, key ideas. Some conjectures initially seem to be valid, but are shown not to be valid after you gather some evidence, right? So, for example, Damara and her lines not equal. Well, we gathered evidence. Guess what, Damara? Those are equal lines, right? Or guess what? There's more than 2 triangles. Or maybe there's not even 2 triangles, depending on which way you visually see it and explain yourself. So sometimes it could be different answers, but a lot of times in math we always have one answer, but there's different ways to get there. Okay? The best way we can say about a conjecture reached through inductive reasoning is the evidence is either there to support it or to deny it, right? But we can't prove it right. We can show that it's wrong, but his statement will stand until someone shows it's wrong, right? And you can revise it if you find issues. A conjecture is a statement that is made, and right now the only statements we've been making is by looking at past examples and making a conjecture or statement. So that in itself is inductive. To look at past experiences or cases and making a conjecture, that's inductive reasoning. Okay? So, taking a look at this circle. We're putting points on the line. So in this circle, I put 2 points, and I can draw one line in between those 2 points, and I get 2 separate regions. Okay? If I take a circle and I put 3 points on it, and I connect the dots, I actually get 1, 2, 3, 4 separate regions. I put 4 dots on it, right? And we play connect the dots, but you can connect any dots, right? So I can connect the dot across, over, and over in every single one. So how many different spots do I end up with? 8. Okay. After looking at this for a while and looking at her chart that she created, this girl made a conjecture. As the number of connected points on the circumference of a circle increases by 1, the number of regions created within the circle increases by a factor of 2. So what does that really mean? That means that when she has 5 points, how many regions is she going to draw? 10. And when she has 6, oh yeah, you guys, 8 goes to 16. Because it's doubling across here, you guys, right? 2 to 4, 4 to 8, 8 to 16, 16 to 32. And then for 7, it's going to be 64 cases, right? How can we verify the validity of her conjecture? Well, you know what we can do? We can test different cases. Let's test 5. This side of the room, you test 5 points. This side of the room, you test 6 points. We cut you right in the middle. Okay, you're 6 on this side, you're 5 on that side. Okay? 2, 3, 4, 5. And I'm not going to lie, it works the best if you have them spread out a long ways and if you use a ruler to draw lines. Two. So you would have got something that looks similar to this, depending on how spread out your dots were, right? So if we count this one out, and usually when I do the count, I write in the space so that when I'm doing the count, then it makes it easier for me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's what we predicted with her thing, right? When we doubled 8, we got 16. So that one's good. What about this next one? Did you guys get something that looked like this? No? Remember you had to connect every dot in line, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. The middle's 31. Did I miss a spot? Huh. We thought it was going to be 32, right? There's a little spot in there under my 31 writing, right? So, you got 31. Did anyone else get 31 when they did their counts? Okay. So, and this is what happens, okay? You can't just disprove once and it, oh yeah, I win, okay? I'm looking through, there's like 8 of us counting this and we're all counting 31, right? Hopefully if they get there, okay? So what did we just do? We just disproved her conjecture, right? By showing step 6. Would you want to draw 7 dots and count it out? No, I probably wouldn't, right? I'd probably, if she was good at 6, I'd be like, you're right, you're good, okay? So, next one. Let's talk about a counterexample. Counterexample is a big fancy word. Is it really fancy? A counterexample is just a word that invalidates the conjecture. It proves them wrong. Okay? A lot of times you guys go, well, what about this in science class? What about this? When we're talking about certain theories or laws and stuff like that, right? That's you guys trying to do a counterexample of a case that might work, right? And then we say, well, mainly this happens instead of it always happens, right? So a single counterexample disproves a conjecture. You may be able to use a counterexample to help you revise your conjecture, okay? And even if you can't find one, it doesn't mean it doesn't exist. It just means you can't find one, okay? So take a look at this cool pattern. 1 times 8 plus 1 gives me 9. 12 times 8 plus 2 gives me 98. 123 times 8 plus 3 gives me 987. Kind of cool. So what kind of pattern is it going to go through? So I could go what? 1, 2, 3, 4, 5 times 8, and then I'd go plus 5 is equal to, and I'm going to guess it equals 98765. Okay? I'm going to give you guys 1 minute. First person to find the counter example, let me know. Try and find a counter example of this. Okay? It's not, oh, like what? 7, 8. Should I stop here? 9 times 8. What are we adding? We're adding the number of things. 1, 2, 3, 4, 5, 6, 7, 8, 9. If I go plus 9, I should get what? 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, once you hit 10 and it starts going to decimals and not even to the right order. Oh.